the quotients, that basic equations that were derived were the vorticity equation, which comes from simply taking the curl of the acceleration. The rest is use of certain basic vector identities. It's a very basic equation where the vector W is the curl of the velocity vector. This is valid for any type of flow, but there is no restriction to either incompressible or linear viscous or any. It just follows from the curl of the acceleration. However, for a linearly viscous, incompressible fluid of constant viscosity, this refers to the fluid. Fluid is incompressible, and further, if the body forces are conservative, we got to the important relation that the curl of the acceleration in such a case is actually the kinematic viscosity times the Laplacian of the vorticity vector. We didn't prove it completely because I said that some of the operations like the curl of the Laplacian can be shown equal to the Laplacian of the curl, and so from that we get this. So then, so when I combine these two, this applied to a incompressible fluid would mean that I can get rid of the rho for an incompressible fluid. So, combining these, like I'm already assuming incompressible fluid, one of the assumptions. So I can use a special case of this equation, so generally incompressible fluid. So if I combine the two, then what would happen is that d by dt, or rather dw by dt minus is equal to, this is a special equation for the special case of linear viscous incompressible fluid and so on. So now the relevance of this, we started out the last lecture by saying that we move from one-dimensional flow to two-dimensional flow, but that's restricted to special type of two-dimensional flow or planar flow. So in rectilinear coordinates, planar flow means there are two components of the velocity, that is two-dimensional flow. Components of the velocity are non-zero. We can choose any one to be v1 and v depending on context. But planar flow means v1 and v2 depend only on x1 and x2. So they don't depend on x3. That is what is meant by a planar flow. For the special case of the planar flow, simplification that will result. So the question is, why do we need the vorticity equation? We partly showed the simplifications that result when we use the vorticity equation rather than the equation of motion themselves directly. So in that case, we showed that W1 is equal to 0 and W2 is also equal to 0. And then W3 will not be 0. That is the component 3 of the curl of the velocity, which you can easily read off to be dv2 by dx1 minus dv1 by dx2. These all result from standard formula. So what will happen is if W1 is 0, let's look at the first and second components of this vector equation. So W1 is 0, so this term is 0. W2 is 0. So how would it look like? So this would look like dW1 by dt is e minus 1 is equal to Cartesian, I think I can easily write without getting into how complicated the Laplacian can be, curvilinear coordinates. Now, so clearly W1 is 0 means this is 0, W2 is 0 means this is 0, and so are the Laplacian of W1 and W2 also 0. The quantities themselves are 0. Now what about this quantity? We take the ith component of this. So this can be written as Wj Ji radial velocity Ji component. And so Wj Ei comma j. This is a general formula. You should never forget these. This is basically the dot product of a vector with a tensor. So now, if I take 1, that would be Wj V1 comma j. So W1 and W2 are 0 already. So those terms will vanish. So let's look at W3. So W3 V1 comma 3 is dV1 by dx3. That's also 0 for planar flow. This is 0. So what about again, W1 and W2 are 0. The only term that we have to look at is j equal to 3. W3 is not 0. V2 comma 3 is dV2 by dx2. That's also 0 for the planar flow that we are considering. So for the special case of planar flow, the two components along the 1 and 2 directions, the equation is a combination of the equation of motion and introducing the vorticity and so on. Everything is combined into this. Those components simply give 0 equal to 0, so they become really irrelevant. Let's consider only the third equation. Let's now look at, if we have written this, what would this be? Also, what? It's 0 because every term has B3 comma something. B3 itself is 0. There's no question of even considering them any closer. So, what we are getting here is that for the third component, this term is 0. What do we have for the third equation? Third equation also simplifies dW3 by dt. So only equation I have to now consider. So on the face of it, it seems to be a differential equation in W3 basically good, but however, we see that this is only the substantial derivative. So I have to now bring it into the spatial derivative form where the velocity of time. What I have is plus this is a scalar equation. So I can apply this formula for the substantial derivative of a scalar. This is what we get. So what is this? This is clearly not quite zero. We don't expect it to be zero because V1 and V2 are not zero. So let's write it out in full. This is V1 dW3 by dx1 plus V2 W3 by dx2 plus V3, that is zero. So this is what this is. And since W3, which is function of x1 and x2 in general, this is not zero. We change, we are getting something which is not zero. So this is not zero. And clearly this is also not zero. This is a Laplacian of some quantity, depends on x1 and x2. So I have to very much consider all three terms. Of course, the steady flow, this would be zero. Steady flow, that would be zero. But we are not now yet restricting to steady flow. So all these, now you notice that it is not simply if we had been able to eliminate the velocities and get only the vorticity, that would have been really wonderful because we just have a scalar equation, the only component of the vorticity, and I could solve for the vorticity directly. But however, that is not the case. I also have V1 and V2 entering the equation. So this is where the whole question. So we have only one equation that is relevant, but we not only have W3, but we also have V1 and V2, three variables. That is clearly not leading anywhere. Having done all this work, we finally get coming to one equation with three variables, which is not really helping us to solve the problem. Solving the problem is finding the velocity profile first. So this is where the concept of the stream function comes in. Stream function is a concept that is applicable for planar flows only. So for planar flows, if you see any either the rectilinear coordinate or the two at least examples of the curvilinear coordinate we have considered, maybe this can be generalized to other curvilinear coordinates. Let's take the incompressible fluid. The continuity equation. This is general form of continuity equation, rectilinear coordinates. Now, when you have planar flow, this term vanishes. Now, what we do with this equation, we introduce the stream function. Here is a couple of ways of introducing. We now introduce the stream function such that sine by dx1. We don't know that function. We are imposing certain relations to the derivative of sine with respect to x1 and x2. So sine is a scalar function of x1 and x2. But we choose sine. Suppose we have a function sine has this property that this is equal to v2 and d sine by dx2 minus v1. So then what happens to this equation? Right, so we can clearly see that v1 by dx1 will be minus d squared psi by dx1 dx2 plus dv2 by dx2 d squared psi by dx2 dx1, which is 0. This definition of the stream function cannot be arbitrary. It is defined in terms of the velocity and then the derivative. So it has to satisfy the continuity equation. Certainly this definition satisfies. Now this you will find the cylindrical also. Take any two, we see that the continuity is split into three terms. each term has only the derivative of the particular component of the velocity with respect to its own coordinate. We have dv rc by drc. We could have dv phi by d phi, but some other terms would come in as coefficients here or coefficient of constant. So this gives the opportunity to define stream functions in different coordinate systems also. So considering only two terms, because of the planar flow, it means two of the velocity components. So we define the stream function in such a way that the continuity equation is satisfied. It can appears to be, can be done for planar flow. The cylindrical spherical wave definitions are very well known. We'll come to them shortly. So this satisfies. Now what this does to the equation? Let us now see what is W3. W3 is d squared psi by dx1 squared. Now using the definition psi. dv2 by dx1 is d squared psi by dx1 squared minus dv1 by dx. So dv1 by dx minus would be d squared psi by dx2 squared. So I get a plus sign. So there is a minus sign here and there is a minus sign there. And now since I am considering only planar flow, where only the two coordinates are x1 and x2 are the only relevant ones, I can also write this as the Laplacian of psi. So now you will see that the whole of this equation, which has three variables, can be written in terms of a single differential equation in the scalar sign. The entire problem of solving the velocity profile now reduces to solving for the stream function. Let's see how, look at the rest of the quantity. So I can now write this as dw3 equal to d by dt of W3 is the Laplacian. It will be quite a complicated equation. Let's now see what this would be. So this would be V1. Everything now has to be converted in terms of psi. V1 is minus d psi by dx2 times dw3 by dx1, d by dx1 of then we have the next term plus d2, which is d psi by dx1 times dw3 by dx2 d by dx2 given by kinematic viscosity times the Laplacian of W3, which is the Laplacian of the Laplacian of psi. It becomes actually a fourth order differential equation in sine. This is the viscous term. These are the inertial terms. So it's a balance between inertial and viscous terms. This is for unsteady state. So for steady state, this would vanish. This is really the inertial term, like the V dotted with gradient of V. It is coming from that effectively. Here we have W dotted with the gradient of V. So if we take the curl of the whole equation, we are getting W instead of V. But this is basically the analog of the inertial term. It is a non-linear term. So now this can be compactly written as, we are not going to worry about the whole equation, only worry about the frequent flow simplification, which becomes very difficult to solve. Now this can be written, you can see that this looks like written in form of a Jacobian. Let me see how I can write this. This can be written as psi as a Jacobian. Jacobian is simply this quantity. So when I write like this, some of you might have heard of the Jacobian, especially used in thermodynamics textbooks. So the Jacobian is just a simplified way of writing. This is basically the determinant I take psi, d psi by dx1, d psi by dx2. You can check that it finally reduces to that. D by dx1 of Laplacian of psi and d by so this is d psi by dx1 and d by dx2 of the Laplacian of psi minus d psi by dx2 times that. This is a very compact way of writing it. But for steady creeping flow, it is one of the most commonly considered cases in textbooks. This reduces to, in itself, this would be quite complicated equation, a linear equation, right? But there is a fourth order equation in sign. We'll see how to solve that. Now, what we will do though is relegate the problem in rectilinear to maybe the assignment, but take up a similar problem in spherical polar coordinates and consider its solution in great detail. Now, if you look at the equation of motion or the equation of continuity, we wrote them in terms of the divergence, the gradients, and so on. We said that those operations can be directly carried over to the curvilinear coordinates. All you have to do is to find out what are the divergence of the vector, the divergence of the tensor, or the Laplacian of the vector, and so on. However, having reached this stage, you might think that this can, all I have to do to reduce the cylindrical or the spherical or any orthonormal coordinate system is to find the Laplacian and the Laplacian square in those coordinate systems. However, that will not be true. That's a warning. You should not directly apply these equations. It have been derived in curvilinear coordinates rectilinear coordinates to curvilinear coordinates. The reason is that it has to do with this important step. The way the psi is defined, this is not in terms of the regular gradient or divergence operator. This definition of psi, this does not directly carry over to cylindrical or spherical. It has specialized to each. So we have to really derive the analogs of these equations in the various coordinate systems, and it also depends on which two of the components are non-zero. That also comes into play. So, if you want those equations, they are actually given in table 421 of first equation. He has given a whole set of how to derive them. If we have time, we will go through it. The derivation will be very similar. As far as the Vorticity equation goes, it is the same as what we have here. This can be easily here. I can replace the Laplacian by the Laplacian in the spherical, polar, or cylindrical, or any other curvilinear coordinate, and all of these operations can be easily carried over. But when we combine that with the definition for stream function, we have to do it separately for each curvilinear coordinate system. So what we will now take up for the present is this very famous problem of a flow around the sphere, and just draw the flow of the same incompressible linearly viscous fluid around the sphere. How to, we won't derive the equation analogous to it, we simply take it. So I have the sphere, let's say radius r, then have the so-called z axis, we can call it x3, with the upward direction. The flow is around the sphere, so this is fluid flowing. And then it goes around the sphere. This is the basic flow pattern. And important is that at long distances we are given from the sphere. V is given to be V infinity times Ez, or if you want V infinity times E3. said as the common notation used in books. If you're comfortable with 3, we can stick to E3. Now you could think, now we consider only the steady creeping flow is all I would consider. The steady creeping flow, if you look at the table, that is the unsteady terms vanish and the inertial terms also vanish. You would expect normally that the equation would be Laplacian square of psi to be 0. But it will not be. Now before we get into that, let's assume that the components that are regarded normally as non-zero are Br and B theta. B phi can be safely assumed to be 0 for this kind of workflow situation. It corresponds to the planar flow of the rectilinear coordinates. So we have this, and now what about psi? If you take a look at the definition of psi, it goes like this. Now the continuity equation corresponding to this, you see the same feature. I have d by dr alone of derivative of dr. Then I have 1 over r sine seems to be a neat way of writing it. I hope it is correct. Equal to 0. If we ask it comes to d by d phi. So I guess because you have the b theta sin theta inside, it might be okay. You can check that this is in fact continuity equation. Virtually every appendix will have this the continuity equation. So that again the same problem. This is dpr by dr. This is dp theta by d theta. So the way to define the very standard definition of discrete function is like this. None of this I am actually giving a proof. So how to arrive at this definition? We see that later. It is possible to infer this in a more rigorous way. We can simply look at the form of this. P r is some function of r and theta, d psi by d theta. D theta is another function of r and theta, and d psi by dr. We call one of the functions f and the other function g. Let's say I don't know how to choose this. So you take that form and substitute it here. You should get equations for f and g, and you will see that there won't be a unique solution, but certainly this solution will correspond to one of the solutions for f and g. That's the one way to proceed. You can try it out, but I'm not going to do it now. Now, what about the equation itself that will determine psi? It will again be a fourth order equation, but it will not be Laplacian of psi equals to 0, but rather this new operator e power 4 psi equal to 0. How is e power 4 defined? E power 4 is e squared is given to be, so when I say e raised to the power 4, is e squared acting on itself. This is the operation. E squared by d r squared plus sin theta by r squared d by d theta 1 over sin theta d by d theta. This is e squared. So e power 4 would be this acting on e power 4 sine is e squared. This another e squared times psi is 0. That's the differential equation. Now, how do we solve for this? Again, I'm not going to give a proof. The proof Again, they follow from applying the separation of variable, but they are not interested in really mathematically solving each and every part or step. So the question is, or the suggestion given is assume that the screen function has this form dependence on r and theta. The dependence on theta is entirely given. Again, if you want to rigorously do it, you would have to use the separation of variables method, and probably the solution of the theta equation would give you this. So we are not again going into the details. So let's take this and look at the solution quickly. So we have to do at least one step. So let's assume this is the case. So what can we say about e squared by d r squared of, first let's take e squared side. E squared is what is given. Before I apply e power 4, I have to first apply e squared and then apply e squared to make resultant. So let's see what we get out of e squared side. Side having this form. So d squared by d r squared very easy to handle. F of r is simply f double prime. The double prime denotes twice differentiation with r of multiplied by sine squared theta. That's very easy to do. Derivative with respect to theta. First I have d by d theta acting on sine. So it would be f of r 2 sine theta cos theta times f of r d psi by d theta. Right? D psi by d theta is f of r, will not be differentiated. Sine squared theta is 2 sine theta times the derivative of sine theta, which is cos theta. Now I have to divide it by sine theta. When I divide it, I get 2 times cos theta times f of r. Again, take the derivative with respect to theta. This will be minus 2 sine theta f of r. Then I have to multiply this by sine theta by r squared. So when I do that, what will I get for e squared sine? Would be f double prime of r sine squared theta plus sine theta by r squared of whatever I have calculated. That will be minus 2 sine squared theta by r squared f of r. Let me now write it in terms of the derivative explicitly. So this is sine squared theta can be taken as common d squared f by dr squared minus 2 f of r by r squared acting on sine squared theta. So now e power 4, we have to apply the same rule, but rather than taking the derivative with respect to theta, there is an easier way. If you look at the structure of this, what has happened is that when e squared acts on sine, which is expressed or taken to be a function of r times sine squared theta, I am getting this whole thing operating on f. So it is equal to another function of r times the same sine squared theta. Now what is that another function? That another function is obtained by taking d squared by dr squared minus 2 by r squared on that function. So that will be e power 4, which will be e squared. So e power 4 sine is nothing but e squared of e squared sine. It is e squared acting on some g of r times sine squared theta. the DFR is given by this. So now I apply the same rule then. E squared acts on some function of r times sine squared theta. I am getting sine squared theta times that function differentiated twice minus 2 times that function by r squared. So I will now argue that e power 4 sine is given by d squared by dr squared minus 2 by r squared, acting not on f but on this, which I have already got one, acting on not on f but on g. What is g? Is d squared f by dr squared minus. The whole thing will be multiplied simply by sine squared theta. Otherwise, if you are not convinced about this, then again you have to do this. Take the derivative with respect to theta and go through the whole process again. You will get the same answer. This is a shorter route to it. If you see the way that e squared is operated on sine, which is assumed to be a function of r times sine squared theta. Now this is somewhat easier to implement. So let's take what this is. So this is d squared by dr squared operating on d squared f by dr squared. That would be d power 4 f by dr power 4. That's one term is taken care of. Then minus 2 times r squared times this. That can also be easily taken care of. Minus 2 by r squared times, because that's just multiplying by 2 by r squared multiplying this. That would be d squared f by dr squared minus f over r squared. But the real work will come at the d squared by dr squared acting on minus 2f by r squared. I have to find that out. D squared by dr squared acting on minus 2f by r squared. What is this? I have to work it out. So let's do that. D by dr of minus 2. Let's take the minus 2 off. So d by df of r of f over r squared is 1 over r squared df by dr plus f times d by dr of 1 over r squared, which is minus 2 by r cube. It is an easier way to do it. Plus f times minus 2 over r cube. So again I have to differentiate. D squared by dr squared of f over r squared is 1 over r squared d squared f by dr squared plus df by dr times minus 2 over r cube and another minus 2 over r cube times df by dr plus f times minus 3 over r power 4 multiplying minus 2 is 6 over r power 4, and then I still have a minus 2 maybe outside. Put all of these together. I'm not going to do it in all its detail, and then multiply it through by, maybe we don't need to multiply. We'll multiply through by r power 4. Suppose I have these and these, this term has to go in here and it's equal to 0. Basically, because e power 4 sine equal to 0 is the equation. So the part of theta is already determined or given to us as sine squared theta. So we're not worried about it. All we have to do is now find f and satisfy the fourth order differential equation. That fourth order differential equation will be given. You can easily show it from these steps that we have taken to be this is again of the same form as we have seen earlier, r squared d squared f by dr squared plus r times df by dr. We have solved it. This only has some additional term. There is no term involving d cubed f by dr cubed. So you don't have to worry about it. So again, solution is taken to be of this form. So I have to differentiate it 4 times actually. Okay, so if I differentiate it once, f prime df by dr is cn r power n minus 1, d squared f by dr squared, cn times n minus 1 r power n minus 2, and the d power 4 would be cn times n minus 1 times n minus 2 times r power n minus 3 or r power n minus 4. So that if we did it twice, n minus 3 also would come in. I'm just skipping one step because I don't need d cubed f by dr, but we have to do that before we get to d power 4. So I'm just skipping that step. You will make mistakes if you are not careful. So I have all this. So let's look at what this equation would be here. So c would come out as a constant, and we get n into n minus 1 times n minus 2 times n minus 3. That's the first term. Minus 4 times n into n minus 1 plus 8 times n minus 8 equal to 0. This is a quadratic equation in n. You can clearly see that n minus 1 can be taken out. You can easily see n minus 2 can also be taken out. Minus 4 times n minus 1. I'm doing this quickly. You have to do it carefully. This is the 4th order equation. So here the solution is quite simple. We get n minus 1 into n, and factorize it out nicely. So we get n squared minus 3n minus 4, and so this would be equal to 0. This is n minus 1 times n minus 2 times n minus 4 times n plus 1 equal to 0. N is 1, minus 1, 2 and 4. The f itself is clearly of this form. C1 I will follow the same notation that I have here. C1 r plus C2 divided by r, that is for r power minus 1 plus C3 r squared plus C4 r power 4. It has 4 constants, and these 4 constants have to be now determined using the appropriate boundary conditions. So the solution of f of r is complete, but only we have to find the constants. So this is a standard again, as this is a very standard equation that appears again and again in the scope. So we know how to approach the solution. You know, it is a bit tedious because it's a 4th order equation. Are there any questions on how we have got here?